Hello everyone and welcome to our next webinar series. I'm Aparna Deshmukh, Technical Director with Next, and I am your moderator for today's session. So let's dive into our webinar titled Non-Metallic Repair Strategies, Advances in Rehabilitation and Strengthening of Reinforced Concrete Using Fiber Reinforced Concrete Matrix, that is FRCM. A PDF of this presentation can be found in the handout box. You can use the PDF to follow the presentation and take notes. You may also use the question box to ask the questions during the webinar, and our speaker will be happy to address them at the end of the presentation. So for continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PDH. Your certificate will be available in ACI University under the certificate tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for one learning unit. Please take note of our disclaimer on the screen for the next webinar series. So now let's begin with a brief description of today's webinar. This live session will delve into the potential of externally bonded fiber reinforced cementitious matrix (FRCM) for repairing and strengthening infrastructure. It will also discuss how FRCM composites enhance fatigue, flexure, bond, and shear capacities in RC structural members, unlocking new possibilities for buildings and bridges. Our learning objectives for this webinar are as shown on the screen. Let's welcome and introduce our today's speaker, Dr. John Myers. Dr. John Myers is a licensed professional engineer and professor of civil architectural and environmental engineering, and he is also the director of the Missouri Center for Transportation Innovation. With over 30 years of research experience, Dr. Myers specializes in high-performance materials, particularly advanced composites and sustainable concretes for structural engineering applications. His research includes a range of technologies including fiber-reinforced cementitious matrix, fiber-reinforced polymers, steel-reinforced polymer, and steel-reinforced grout, focusing on their use in repair and new constructions within civil engineering infrastructure. He has been contributing to the code standardization for many years. So Dr. Myers has authored over 300 technical publications and holds leadership position in several professional organizations. Additionally, he brings over 11 years of professional consulting experience and holds the title of fellow in ACI, ACE, IAAM, IIFC, TMS, and West. So let's welcome him and listen to his presentation today.
Thank you so much again for that very kind introduction. And again, my name is John Myers. I'm a professor at Missouri S&T, and I'm really, really pleased to have this opportunity to present as part of the next webinar series. Before I dive into the presentation, for those of you that are maybe not too familiar with Missouri S&T, we are one of the 4 campuses in the University of Missouri system, and 2 of our first graduates in civil engineering date back to 1870, so we're really proud of our rich history. And for example, this past year we produced the 18th most civil engineering graduates in our nation. We're located between Kansas City, Missouri and St. Louis, Missouri, but along I-44, as you can see there in the map. As Aparna mentioned, I also serve as director of our Missouri Center for Transportation Innovation, and I just want to mention that because much like ACI Next, we're very, very interested in deployment, implementation, and advancement in innovative research, including what we'll be talking about today. And we're always very, very interested in collaborating with other organizations. So if there's an opportunity to do so with any of our 4 campuses, please do consider that and reach out to me. Now today we're going to dive into the presentation that was mentioned. And first of all, remember what FRCM is. It stands for Fiber Reinforced Cementitious Matrix. And in this slide, I'm going to highlight the process to install FRCM systems. First, the surface is prepared to open the pore structure of the concrete, followed by a base mortar, then a cementitious mortar. Then in this case, we're looking at the use of a PBO fabric system as the strengthening system intention, followed by another layer of mortar. And these last 2 steps can be repeated if there's multiple plies. In this research, we're going to be talking about comparing 1-ply system with actually 4-ply systems in some of the research. I'd like to contrast FRCM to more traditional FRP systems that many in the audience are familiar with. FRP, or fiber reinforced polymers, utilize typically glass, basalt, or carbon fibers, for example, in a resin or epoxy binder system. ACI 441R, as you can see here, dates back to the late 90s and is an ACI guide for the design of FRP for new construction. And you can see when we talk about new construction, we're typically talking about internal reinforcement with these FRP products. But ACI 442R is an ACI guide for repair systems. And again, as you can see here in the repair application, the carbon fiber sheet in this particular case uses a epoxy resin system as the adhesive and binder. So I just want to kind of contrast the cementitious based that we'll be talking today a little bit more with the more traditional FRP systems. For FRCM and SRG, SRG stands for Steel Reinforced Grout Systems. There are 2 ACI guide designs that are out there, ACI 549 4R, as you can see here. And again, this is a system we'll be talking about in today's webinar. And also ACI 549 6R, which focuses more on masonry systems. And today, again, we're focusing on FRCM on the left, but as it relates to concrete structures, but I would be happy to present and talk about masonry in a future webinar if so desired. Repair and strengthening is often required for different reasons, could be due to deterioration, accidental, either man-made or natural disasters, historical importance. In our home state here in Missouri in particular, when we talk about infrastructure, we have many of the bridges built between 1930 to the 1950s that are structurally deficient. So over 1,400 here in Missouri. Again, this is not necessarily tied specifically to bridges only, but infrastructure and buildings as well. And nationwide, we have as many as 63,000 that might need repair and strengthening. In the 1990s, when FRP was really, products became more widely evaluated and developed in Europe, US, Canada, Japan, and elsewhere, these products typically came in bar, strip, grid format, as you can see on the left. And while this remains a very promising repair strategy, one of the challenges is that the epoxy resin has some limitations in terms of higher temperature applications due to the glass transition temperature of the resins. And you can see on the right-hand side some of the applications that these systems have been used for, either repair or new construction. Therefore, the development of FRCM systems provides some advantages compared to the aforementioned products, and some of these include the same resistance to high temperature as the substrate, compatibility of inorganic materials to damp structures, and actually, as we'll talk about, the presence of moisture can actually provide some post-cure enhancements to the cementitious-based binding system. Ease of installation is another advantage. It's less toxic than some of the chemicals used for FRP repair systems, for example, and also you have the ease of reversibility. We're going to be talking about the PBO fabric shown in the center upper side, but of course there's other fiber systems that can be used with this inorganic type matrix. In our research program, we examine gaps as highlighted in red. And in particular, if we work from left to right, you can see fatigue, environmental exposure, shear performance with and without internal shear reinforcement. Again, evaluating environmental exposure for some of these systems, and also looking at the durability side of environmental conditioning using a pull-off and bending test, and then also some anchorage type systems, two in particular. So some of these boxes in blue were some of the first initial studies on the topic that we were aware of when this was undertaken, and particularly on the fatigue and environmental exposure and the anchoring systems. So our research work was subdivided into 5 tasks, and this presentation or webinar is formatted as such. Task 1 is looking at the fatigue and flexural behavior of reinforced concrete beams strengthened with FRCM. Task 2 is a shear strengthening of reinforced beams with FRCM. Task 3 looks at flexural strengthening of one-way slabs with 3 different repair systems. Task 4 looks at the durability performance of FRCM through 2 different tests. And Task 5 looks at the anchorage for enhancing FRCM mechanical performance, particularly in a debonding sensitive scenario. So let's dive into our first topic, which is looking at the flexural and fatigue performance of these systems. And when this was done, it again was the first study that I was aware of looking at this combination. That combination includes to evaluate the fatigue resistance of this new FRCM system, subjecting the test specimens up to 2 million fatigue cycles, and secondly, investigating the durability of the FRCM composite subjected to environmental conditions. And for those of you that work in durability of composites, typically the big 3 are temperature, moisture, and stress that we looked at. This table shows our test matrix, and the variables included the environmental cycles with and without stress, external natural exposure, number of plies. We also looked at, as well as the frequency of the fatigue testing. I want to mention, as you see in this plot, we looked at 1 and 4 plies. It may be noted that a collaborating institution, the University of Miami and Tony Nanny's group, complemented what we were doing by examining 2 and 3 plies concurrently when this research was done in the laboratory. So we went 1 through 4. Our testing focused on 1 and 4 plies. In the direct tension test, there is a bilinear nature of these FRCMs as shown in the plot, and this includes a linear elastic behavior until at this stage until the cracks actually form. Once the cracks form in the actual matrix, then it's the fiber that is carrying the load, of course. And this is the properties of for the study are shown in Table 1-2. The mechanics involved includes the contribution of the steel and that of the FRCM repair system. The repair system not only adds additional flexural capacity from the steel or the existing strengthening system, of course, but it also adds the additional capacity of the external repair system. It may be noted that additional displacement ductility or energy to the system is represented, as you can see here, as area B. And so our work really examined the stiffness, strength, and ductility of these repair systems. Here are the details of the reinforced concrete member, including the mix design, the FRCM matrix, and the rebar as shown. For these repair studies, what we try to do is utilize mixed designs that are vintage of the type of concrete we would be trying to repair in the field, both in terms of what's used in the mixed design. So we wouldn't necessarily be using today's admixtures. And also we would be trying to develop properties, including the compressive strength, that are representative of field repaired structures. You can see the details on the beam here and the reinforcement that was used. Again, the reinforcement level would be representative of what we would expect to see in an element in the field. As part of the environmental conditioning, an environmental chamber was used with the conditioning protocol shown here on the right. This accelerated regime simulates between 10 to 20 years of Midwest U.S. exposure to align with the desired service life for most repair systems. And so, for example, if we would be repairing a structure in the exterior environment, let's say it's a parking garage, let's say it's a bridge, when we talk to our Department of Transportation, they would be delighted if they could get 10 to 20 years of extended service life out of that structure. Below, in the lower left-hand side, we also had beams that were placed in a natural environment that we currently have that we can do longer-term, multi-year tests on to evaluate. It's important to note those specimens are not under sustained stress, though. This slide shows the fatigue test setup and the fatigue cycling. The maximum load represents approximately the service level of the repair system that we would expect. And it may be noted that the level of stiffness loss is rather minimal, as shown at the bottom right, from the first 10 cycles to 2 million cycles. If we look at that in a histogram plot, here you can see this in terms of 250,000 cycle increments. And here we're looking at the one-ply system of FRCM. It may be noted in general that there is a minimal drop in the stiffness as cracks continue to propagate and develop, and then the stiffness stabilizes. You can see color-coded for control specimens, lab specimens without stress, environmental condition specimens without stress, with stress, as well as the external specimen in the outdoor environment that is unloaded. For the 4-ply system, we see a similar trend. In this case, the loading is, of course, higher because the reinforcement added to strengthen the beam utilizes 4 plies, and that higher load level, the beam without any strengthening in blue, you can note that that one actually failed during the fatigue cycles past 1,500,000 cycles. Only the control specimen without the strengthening system failed due to the fatigue testing, and all the remaining strengthened specimens all survived 2 million cycles. And there again, you can see the degradation in stiffness early on during the fatigue testing, and the failure of the control specimen without any strengthening system. This figure shows the strain reading at the maximum fatigue loads, and clearly, if we take a look at the strain levels measured in both the steel internally and the FRCM externally, you can see that the FRCM system is carrying its load similar to what we would expect in the strain and stress distribution. So this confirms that the system is actively functioning and carrying the load. In all cases, the FRCM system improved the load carrying capacity compared to the beams without FRCM. So in this plot, first on the left with the one-ply system, the blue line in all of our results I'll be showing you represents the control specimen without any strengthening. And so you can see that any of these beams conditioned in any environment all showed an increase in the one-ply system. It may also be noted that the exposure conditioning in the environmental chamber improved the post-set cure of the cementitious matrix, so that availability to moisture and the cementitious binding system continued to strengthen the bond performance when subjected to moisture. So this is an important item to note. In the 4-ply system, you can see that we also improved the strength carrying capacity when all of these beams were tested to failure after fatigue loading. But note that we do not receive a 4-fold capacity increase because these beams all failed by debonding. And so it's very important to note the difference in the failure modes for 1-ply versus 4-ply. In 1-ply, we see a fiber slippage failure versus a debonding failure. And I want to focus on this because towards the end of the presentation and webinar, we're going to talk about the importance of anchorage systems and how they can help delay that debonding failure for multi-ply systems where we would expect debonding failure to govern. Comparing the experimental results of testing capacity at failure to theoretical values using ACI 549, we see that the factor of safety was over 100% as shown here for 1-ply and over 30% for 4-plies. Again, for 4-plies, we have that premature debonding failure as the governing capacity as the strain level and the reinforcing level is higher. So for task 1 conclusions, we see that fatigue and flexure tests revealed the effectiveness of the PBO FRCM composite in restraining the reinforced concrete beams against greater fatigue crack development. We noticed that there was a reduction in stiffness, 10 to 30%, and also an increase in flexural enhancement from 25 to 60%. That's important because a lot of field projects, we might be looking for anywhere from 10 to 20% flexural performance enhancement. Also, all the beams lasted for the 2 million fatigue cycles without any debonding during fatigue testing of these strengthened beams. Environmental exposure did not affect the beam's failure mode. The sustained loads reduced significantly the beam stiffness by as much as 30% as crack formed in the matrix and softened the member. So it's not necessarily the crack development as much in the concrete beam, but in the matrix itself. Using 4-plies systems had a great influence on the fatigue performance and the flexural performance. So that enhancement, as mentioned, was 40 to 60%. And the flexural capacity was not affected by the long-term fatigue loading. So let's dive into task 2, which now looks at the shear behavior of FRCM. And let's look at the objectives of this part. This part was to look at the shear performance of reinforced concrete beams, strengthened with externally bonded PBO, FRCM, in the availability or absence of the internal transverse shear reinforcement. So we were interested if there was a difference with and without internal shear reinforcement. And we're also going to compare the ultimate shear loads of the system with theoretical shear loads using ACI 549 and previous experimental work with FRP systems. In the analysis and design approach for FRCM, a shear contribution from the FRCM is added to the contribution of the steel, as you can see the VF at the bottom of the member. In this work, we examine the behavior with and without steel stirrups, as I mentioned earlier, and we also looked at the type of shear reinforcements, continuous versus using strips, as well as the number of plies, 1 versus 4. Here is shown the profile of the beams, first with internal steel reinforcement, as well as without. Again, the mixed design that we used was representative of what we would expect in the field for an older structure that would be a target structure for repair. In this work, a shear span to depth ratio A/D of 2.5 was selected. No strengthening naturally was applied between the points of loading where only the shear load exists. In terms of the beam self-weight is the only shear load in the middle of the 4-point load testing. So there you can see the configuration. And again, set A is the beams with internal stirrups, and set B, as I'll show you in the next slide, are the beams without internal stirrups. So now let's examine the results in shear. First, for set A, as shown at the bottom with internal steel, we can compare the capacity of the beam with the steel stirrups and the concrete. Again, the blue line is the control specimens. And we can see that all of the beams had an increase in shear capacity due to the strengthening of the system. However, there was a significant difference between continuous FRCM shear reinforcement versus strips. The continuous had a greater ductility added versus the strip reinforcement that was used. So you can see the benefit of using continuous shear reinforcement of FRCM. If we look at set B, the only contribution we have here is that of the concrete, and then the addition of the reinforcement from the fibers. For set B, without the presence of the internal steel reinforcement, we see that the FRCM strengthening system is much less effective in this experimental lab work, which was a major takeaway from this work. As shown here, the current ACI design predictions are all very conservative. If we look at first the steps with stirrups, the increase range from 60 to 120% with stirrups and without stirrups, and with stirrups 50 to 230%, as you can see. For the beams, again with internal stirrups compared to the control beam, the continuous enhanced shear performance was by 20 to 30%. So from a code perspective, very conservative. From an actual increase perspective, 20 to 30% with stirrups. And then without stirrups, it was only 10 to 20% range. And keep in mind, of course, whenever we do shear testing, it is quite variable. And so we didn't do many replicate testing on this to really look if it was just kind of an outlier or not. But again, there we can see that gain in capacity by using the FRCM in shear. So for shear, the strengthened beams with internal shear reinforcement had a significant increase. For the continuous FRCM, it was 24 to 32%. For the discontinuous strips, it was only as much as 18%. The continuous U-wrapping revealed better ductility though, 1.5 times that of the discontinuous strips, as we saw in the figures. The strengthened beams without internal shear reinforced exhibited a more brittle failure mode with no significant increase in shear load, although, as I said, probably more experimental work is needed to understand and address this case scenario. The absence of internal shear reinforcement, the non-homogeneous property of the concrete, and the fragile cementitious matrix produced an unexpected crack width and pattern that contributed to lowering the effectiveness of the PBO FRCM system in shear strengthening. And then finally, relative to the code, we saw that there was a 1.6 to 2.2 conservative nature in terms of what's predicted versus what we found experimentally. And also the PBO FRCM strain validated the effective strain limit of 0.004 at failure. And then comparing with previous experimental work, this revealed that FRP systems are more effective than the PBO FRCM systems for shear enhancement of reinforced concrete beams. So from FRP, we might expect 50 to 100% increase. From PBO FRCM, it was only 20 to 60%. So again, I'll use the old adage, we have different tools in the toolbox, something I like to steal from Tony Nanny, and you can use the most appropriate tools for the application that you're looking at. Now in task 3, and the last few tasks will go a bit quicker, we're looking at examining the behavior of reinforced concrete one-way strengthened slabs using different composite systems. So these 3 systems that we looked at and compared were first the PBO fabric that we looked at in shear and flexure and fatigue. Number 2 is a carbon grid with epoxy paste curing agent. So here we're comparing a one-way slab with a cementitious, but a different fiber with an epoxy paste curing agent. And then 3 is a steel reinforced polymer. And it's important to note these are galvanized high strength steel wires. In case you're wondering, why would I put this material close to the soffit where corrosion might be an issue if the material matrix is very permeable to moisture. The variables we looked at in this phase of work looked at the number of layers, so 1, 2, 3, and one layer was done in the environmental chamber for looking at durability. The exposure condition, as mentioned, so either the lab or in the environmental chamber, as you saw earlier, and then also the reinforcement ratio to try to keep the expected load carrying capacity relatively similar. Again, the mix design here, as mentioned earlier, was used to be representative of what might be repaired in the field in terms of a slab or a deck. And here you can also see the setup of the specimens. So let's take a look at the results here. And first we'll look at the results of FRCM composite on the left. And again, remember that the blue line represents the unstrengthened slab system. And so when we look at the system in terms of one ply, a one-ply system again had a fiber rupture failure mode when looking at FRCM, while 2 and 3 plies debonded, and that occurred for 2 and 3 plies on the one-way slab. It may be noted again that in the environmental conditioning for the specimen that was subjected to the environment provided that additional capacity and additional ductility due to the post-cure effect of being in a moist environment as well as the temperatures that was in that environment. If we look at group 2 now, we see that the CFRP fiber, which has actually much more greater tensile capacity, did not necessarily result in improved capacity, or for that matter, it didn't result in the best post-peak behavior. And then finally, for the one-way slabs with SRP, in terms of the epoxy curing agent, it did provide better capacity, although the tensile capacity of the steel is higher. But then it also provided a little bit better post-peak behavior. And none of these systems we saw significantly degradation in, which was a good finding as well. When we look at now one-ply systems with just the load displacement curve here in terms of reduction of capacity, the color coding shows all one-plies in the environmental chamber. Again, we see little effect for the SRP and the CFRP systems, with an actual improvement in the FRCM system due to that post-cure effects. So that's one advantage we saw or observed of the 3 different systems here. And again, the reason we were looking at this was to look at and see what might be an appropriate C sub E factor for 440 or 549 for the use of these materials. And again, there you can see the difference in the red system, which is the G3 system using the SRP system. And the only, again, degradation we saw, no significant degradation for the one-ply conditioned. As illustrated in this slide, we can see that ACI 549 and also 440 for System 2 standards are all conservative, which is good. The safety factor was generally 1.6 to 1.3 for one-ply to 3-ply for the FRCM. The steel reinforced polymer system had the lowest safety factor in this study, which you can see highlighted in blue. So that's also an interesting finding, that it's not as conservative. Again, for all these one-way slab systems, they can be improved by using FRCM, CFRP grid, and also SRP composites. And the increase in normalized ultimate loads of the strengthened slab averaged between 1.3 to 2 times that of the unstrengthened slabs. The impregnation of the PBO fabric with cementitious matrix exhibited good flexural behavior with respect to FRP composites, and the composite properties, the composite material type, reinforcement ratios, and mesh spacing all played an important role in the flexural behavior of strengthened systems for these RC slabs. And finally, the sensitivity of the epoxy curing agents to high temperature was observed as the as the exposed reinforced concrete slabs determined lower ultimate capacity, 10%. And then we saw that the codes and standards were conservative, but on the SRP system a little bit less so. Now we'll move quickly into task 4, which is looking at the bond performance of these systems. And in task 4, we examined the durability performance of FRCM under varied environmental aging conditions. And these are durability and condition exposure tests using the ACI 449R document. So basically using the beam bending test on the left and the direct tension pull-off test in the right. So for the pull-off test, as you can see here, in this test, within this test, we used 4 exposure conditions that we considered, and this included environmental conditioning cycles, 100% relative humidity, salt water, and alkaline solution, and again, using the ACI 440 document. For the bending test, again, 2 main variables were considered, the level of surface roughness, and the environmental conditioning. Again, the ACI 449R document was used for specimen size and testing protocol. The direct pull-off test is a highly variable test if you have not done it before, as shown by the scatter of test results in the plot. However, it does provide important details in terms of where the failure mode occurs. So whether it fails in the substrate or whether it fails within the strengthening system, as you can see in the bottom right. And you can see here that this failed in the PBO fiber and substrate. Results from the beam bending test also indicated that a lighter roughness, ICRI roughness preparation was better than a rougher performance in terms of bond, and it produced better bond behavior, similar like we would see in an FRP system using epoxy. The environmental conditioning did not have a significant impact in the beam test. So in terms of the two test methods, it revealed that the bending beam test is more representative of bending beam behavior than the pull-off test. Comparing between the bending strength with tensile coupons of FRCM revealed a good agreement in the ultimate strength and ultimate strain of the PBO fabrics. So the beam test worked best there. And also the beam test resulted in the same mode of failure as we saw in the larger tests that were undertaken in the beams, in the larger scaled reinforced concrete beam test. So that was also very important correlation between the two. In the pull-off test, the pull-off load was applied perpendicular to the PBO fabric alignment, as you saw, where the bending test puts the specimen applied parallel to the PBO fabric alignment. And that concluded that the observed higher strength in the FRCM composite and bending test rather than the pull-off test itself. Finally, we'll move into the last task, which was looking at anchorage system. We wanted to examine how anchorage systems might be able to delay a slippage failure or a premature debonding failure. So we examined two possible anchorage details, including a novel approach that we developed at Missouri S&T in this work. Here you can see the concept of an anchorage system under normal load. Externally bonded systems want to debond. The concept of the anchorage system is to delay any premature failure of the external system and thereby increase the load carrying capacity. You'll notice with our system, we also want to install the system in the compression region of the beam. And we'll talk more about that. First, in terms of the test matrix for this work, it included a control specimen shown here, as well as two specimens, one with 2 plies and 4 plies respectively. Recall that 4 plies resulted in a debonding failure in flexural testing earlier, while 1 and 2 plies, remember the 2-ply test was done at the University of Miami, both failed in a slippage failure. So what will this tell us about slippage failure and debonding failure and the necessity for using an anchorage system? Again, this gives us a detail on the number of anchorage, and the two different anchorage systems, again, were a spike anchor as well as the PBO anchorage system we tried in this particular work. Reported in this slide are the concrete mix designs, again, representative of older concrete in the field. And also note the cross-section and reinforcing details as shown. The first type of anchorage system is called a spike anchor. This detail was investigated in the 2000s at Missouri S&T and elsewhere, I'm sure, for use in the manual wet layup CFRP epoxy system. And here you can see in terms of impregnating the spike is inserted into the soffit of the concrete. It's wrapped up because we feed this through the PBO fabric, and then, of course, fan it out, and then put it on top of the final placement of the cementitious mortar system. So this is the glass spike anchor system, and on top is shown where the anchors were applied. And then the second type is this innovative anchored system that we call the UWrap PBO strip, developed at Missouri S&T for the study. And one of the advantages of this is, again, note that this is also a steel-free detail to avoid any corrosion or use of any metal products, to have that help extend the service life. And again, also note that we developed this detail in the compression zone up here. So again, similarly, we impregnate it. In this case, we're using an epoxy. And again, this wraps around the system, again, to help try to prevent a premature debonding type failure. So let's take a look at the results, and this reports the load deformation response for both the 2-ply and the 4-ply anchored systems. Remember, in the 2-ply system that we expect to have a fiber slippage failure and not a debonding failure. You can see the blue line represents the unstrengthened, and then you see the green, purple, and red lines. Know that the red line is the beam without a strengthening system. And what do we see there? We see that there is no real impact of using an anchored system when we have a fiber slippage failure. So the big takeaway here is, unless you expect a debonding failure, there's no use or purpose in using an anchoring system to increase the capacity. However, when we look at the 4-ply system where we see the debonding type failure, now we start to see the capacity of the beam without any anchored system. Then we look at the spike anchor system in green. We see an improvement in that system. And then finally, when we go to using the PBO system developed at Missouri S&T, we see the greatest increase in capacity. So again, the takeaway here is, when we have the debonding failure, any type of these anchored systems is effective to delay a premature debonding failure, give us better ductility, and give us additional capacity. So just remember, fiber slippage, 1 and 2 plies in our work, and above that was a debonding failure. So our takeaways for this last final task is, again, that the anchored systems are effective depending on the failure mode system, but these are also be effective based on the reinforcement ratio, and most importantly, the mode of failure. No influence with the 2-ply system where we had fiber slippage failure, but very effective for the 4-ply system. In terms of enhancement, what we saw for using the glass spike anchor with 4 plies, it was a 10% increase in enhancement. And for the anchored PBO system, it was an additional 24% enhancement using that system. And this brings me to the conclusion of the presentation. And as with all research, many contribute, and I would like to thank and acknowledge this list of individuals, and also this list of sponsors and center support that we had for this work. And very, very appreciative to have this opportunity to present to NEXT as part of the webinar series. And last but not least, I would like to thank Zena. She's a professor now back in Iraq, and she was the one that did all of this work along with the other folks mentioned and shown. And you know, they always make us as professors look good. So much appreciation to Dr. Zena here. And that does bring me to the conclusion of the presentation. And I think we have a questions and answer period here. And do you want me to stop sharing, or you're going to do that, Aparna, I think.
Yeah, it's fine. For now, we can just have it so that if there are any questions, you have to go back and forth and see the
Okay.
slides. You can always do that. So thank you so much for the outstanding presentation, John, and thank you also for sharing your expertise and also sharing this intriguing results, which comparing different systems of non-metallic strengthening. Yeah, let's move to our question answer session. Our first question is, are there any specific environmental benefits or considerations associated with the use of FRCM in concrete repair and strengthening?
Yeah, that's an excellent question. So, I mean, I would say that from my perspective, FRCM is probably a little bit more sustainable in the sense that if you look at the manufacturing process of a lot of the heavy chemicals that are used in a lot of the straight FRP products, those tend to use, more harsher chemicals. They're a little bit more toxic. I think, if you look at the footprint of any material we use as structural engineers or material folks, I mean, there's always some sort of carbon footprint. So it's, whether you're using steel that has to be extracted and mined and then processed, that all takes energy. If we're just kind of comparing the two, I mean, some have benefits. I think the benefit here of this material is that you're using a similar adhesive or binding system as the substrate material, since it's reinforced concrete and you have concrete there. And probably the chemicals are a little bit less toxic. So I think from that perspective, I would say FRCM has a little bit more benefits in terms of the footprint, perhaps.
Yeah, as you talk about footprint, the next question is how does it compare on the base of long-term durability of FRCM
Right.
compared to the
Yeah.
traditional repair materials? So does it?
Well, that's a great question. So one of the points I would make, if we're going to use this system in flexural behavior, or we're going to use, let's say, a CFRP that's impregnated with epoxy. First of all, the carbon system with epoxy that we would be more traditionally used to using ACI 440, for example, is going to give you more strength. It'll give you better shear behavior. So a lot of it gets down to, as a structural engineer, what capacity enhancement do you need? If I'm looking to repair something that, again, if it's a Department of Transportation or a building owner, and it's in an enclosed environment, I mean, that service life's probably going to be a lot longer because it's not under harsher environmental conditioning. But it gets down to what is your intended extended service life. If it's 10 to 20 years, which was the example I used that, for example, our DOT may be looking at before, decommissioning of a structure and replacement. And a lot of times replacement, and if it's a bridge, that may be driven by, I need more lanes of traffic, so I need more volume capacity. That may be a reason, not necessarily how well the durability of the repair system stands up. But I think whether you're using FRCM or whether you're using an epoxy-based repair system, I mean, either one is going to hold up, I think, if it's a target, let's say, of 20 years. Now, we didn't look at extending that 40 or 50 years. We could have, with funding, maybe extended it, ran a lot more cycles and see if it still holds up as well, see if there's further enhancement and post-cure effect of, bond strength of the cementitious materials. That's a little bit of an unknown. But again, I think it kind of gets to the needs of the owner. If you're doing something for a parking garage, for example, that may be a different case where maybe you want 40 years additional service life. And so I think more work could be done looking at, trying to represent lab tests or monitoring projects in the field, which is an important thing that we need to think about when we deploy all these non-metallic materials in the field, whether for new construction or for repair, is to really be mindful and go out there and inspect them and see how they're performing.
Yeah, so it's very application based.
I would say so, yeah.
Our next question is, what ongoing research or developments are taking place in the field of non-metallic repair strategies, particularly in relation to FRCM technology? So, I mean, where the research is right now.
Well, I think that's a good question. I think perhaps FRCM also, I think, has a very good application to masonry upgrade, masonry repair. I didn't talk about that today, but I think that's probably a good niche application, especially for historic structures. There's always some questions about how do I do this without, detrimentally affecting the aesthetics. When we talk about repairing of masonry systems, for example, but I think that's an application that I think is an area where some additional research can be done. There's a lot, I think, being done there on confining columns, particularly in Europe, where there's seismic upgrade needs. And just in general, I think we can try to understand more about developing some of these standards for seismic enhancements and improvements. Excuse me.
Yeah.
So,
Yeah.
so I would say those are some areas for FRCM in particular to look at.
Okay, thank you. So our next question is, what are the potential failure modes of anchorage systems in FRCM retrofitting, and how can they be mitigated through design or material selection? I know you had a slide where you explained about the anchorage system, so can you please elaborate on it?
Yeah, so failure in the anchorage system, that's an excellent question. A lot of times what we've seen in our lab tests is we didn't necessarily see a failure in the pull out of the anchor itself, but we saw a debonding initiating between some of the anchorage locations. So that sort of precipitated the initiation of a debonding failure. If you design the system properly, where your anchor has enough tensile capacity, usually it won't be the anchor itself that's pulling out or failing. It could be if you don't use enough of an anchor and it's not necessarily anchored well. But typically, a lot of the epoxy type anchor systems we use have very good tensile properties, and you're still going to have oftentimes a debonding failure, but that will be a later debonding failure, I guess is a way to put it, where you sort of avoid that premature failure. But, again, it will have to do with how closely spaced the anchors are and how you design that anchorage system. And I think as far as some of our standards goes, that's probably an area as well for further research to come up with better design practices for anchorage systems, particularly for FRCM.
Okay, great. Thank you. Yeah. Our last question is, what are the most suitable testing methods and standards for evaluating the bond strength and mechanical performance of anchorage systems for FRCM applications? Yeah.
The best testing method? That's a really
Or
good question.
most suitable. Yeah, yeah.
You kind of stumped me a little bit on that one, because I would say that the specimen you would ideally like to test would try to replicate the loading configuration and the stress distribution and strain distribution that you would see in a real world application. So the ACI test that I showed you that we used, for example, just to look at bond performance of the system, that really isolates the bond performance of the repair system. And so perhaps it would be something where, it's a concrete prism, it's in flexure, and you're trying to evaluate the holistic system in terms of with the anchorage. And then, of course, you could also try to do some evaluation of just maybe pull out of the anchorage itself. So maybe there's two test systems that could go hand in hand there. And you try to isolate the individual components of the anchorage system. But I don't know that a lot of work has been done other than, we did some tests here in terms of environmental exposure, but then the next question might be, how long do these anchorage systems perform well for example. But I think that's a really good topic for the two ACI committees to kind of maybe ponder a little bit. I know ACI 440, has a task group looking at anchorage and having more information developed in some of the ACI 440 documents. So I'm less engaged with 549 though on that issue.
Yeah, no, great, great. Thank you so much. I guess with this, we end our question answer session. Thank you again for answering all the questions. And before we go, we have an announcement. I'm sharing my screen. Yeah. So, like every year, Next has opened its call for ideas for 2025 funding. Please submit your ideas by May 31st, 2024. The submission guideline and fillable submission form can be found on Next website. Just go to www.nonmetallic.org/next projects. You will find the submission form as well as the submission guidelines. And this is the list of the upcoming webinars at ACI University. Please visit aciuniversity.com to register the upcoming webinars. And once again, thank you to all participants for joining our today's webinar. We look forward to having you with us again in our next webinar. Have a good rest of the day. Thank you. Thank you, John. Thank you so much.
Thank you.
Yeah.